Hi, today's lesson is on probability. Probability is the mathematical study of chance. Chance is a term we use casually in everyday conversation. It could have many meanings. I could say, the chance of rain today looks like 25%. Or, there is really no chance that my friend is going to turn up since it's raining. Or, there's very little chance that India is going to win this match now. So, to systematize the theory of chance in a mathematical way, we learn probability. Of course, we cannot just talk about the probability of anything. It has to be able to be studied in a very systematic manner and the ground rules laid down. In this lesson, we will begin with some simple examples which can be shown to have a probability. Then we study the language of probability, the precise language that allows us to find probabilities of certain events. Then we move on to slightly more complex problems, which involve permutations and combinations. And finally, we discuss odds. So let's look at a very simple example. A bag contains 3 red balls and 4 green balls. You draw one ball out of the bag, without looking, of course. What is your chance of getting a green ball? To find the chance of getting a green ball, obviously, I need to know the total number of balls. The total is 3 plus 4 equal to 7. So the chance of getting a green ball is 4 out of 7. Similarly, what's the chance of getting a red ball? Well, there are 3 red balls out of 7. So the chance of getting a red ball is 3 out of 7. Your dresser contains 5 red shirts, 2 blue shirts and 4 white shirts. You randomly pick one shirt to wear. What is your chance of picking a blue shirt? Again, you have 2 blue shirts out of a total of 11 shirts. So your chance of picking a blue shirt is 2 out of 11. A red shirt, you have 5 red shirts and there are 11 shirts in all. So 5 out of 11. How about the chance of picking a white shirt? Yeah, there are 4 whites. So 4 out of 11. Of course, 5 plus 4 plus 2 is 11. So the chance of picking one of those shirts has to be 11 out of 11. So a fair die, that's a number cube numbered 1 to 6, is thrown. What is the chance of getting the number 3? So when a fair die is thrown, it falls face up on any one of the 6 numbers. What is the chance of getting the number 3? Well, 1 out of 6. The number 0 does not occur on the fair die, so there is really no chance of getting the number 0. So we say the chance of getting the number 0 is 0 out of 6, or just simply 0. Which means there is no chance of getting the number 0. The next example. Set S is the set of all numbers from 1 through 100. What is the probability that a number randomly selected from the set S is divisible by 3? So, we are picking one number from 1 through 100. So, there are 100 choices to pick from. How many of these choices are divisible by 3? So, there are 33 numbers divisible by 3 between 1 and 100. The numbers 3, 6, 9 up to 99. So, the probability of selecting a number divisible by 3 is 33 by 100. The answer is B. Having looked at these simple examples and got a feel for what probability means and how we go about calculating simple probabilities, let's now learn the formal language of probability. So the first thing that we need to understand, that we are trying to find the probability of something that happens. That something is an experiment. So we are always conducting an experiment. The experiment can be something simple like picking a ball out of a bag, or picking a shirt out of a drawer, or throwing a dice, or tossing a coin. That is the experiment. It's important to understand that if you have a bag of balls and you're picking one ball, that is one experiment. If you're picking two balls, that is a very different experiment. Similarly, if you're throwing one dice, that's one experiment. If you're throwing two dice and looking at both the numbers, that's an entirely different experiment. So having conducted the experiment, what are you looking at? You're looking at the outcomes of the experiment. So, what are the outcomes when I throw a number cube? The outcomes are the numbers 1 to 6. There are 6 separate outcomes. What's important about these outcomes is that they're all equally likely. There is an equal chance that the number 1 falls, or the number 2 falls, or the number 3 falls, and so on. Which is why we call that die a fair die. It is implicit that all the outcomes are equally likely. Similarly, when we pick a shirt out of a drawer, we are assuming that it is equally likely that we pick any one of the shirts, any of the red shirts, any of the blue shirts, and so on. What is the sample space? The sample space is the set of all outcomes. Which is to say that again, if I throw a fair die, then my sample space consists of the numbers 1, 2, 3, 4, 5, 6. All the possible outcomes of that experiment constitute the sample space. What is an event? An event is those set of outcomes which satisfy what I want. So if I throw a die, the sample space is 1 to 6. I could ask, what is the probability of getting an even number? So the event is obtaining an even number. So the event is the outcomes 2, 4, and 6. An event is a set of outcomes which is a subset of the sample space. Recall the shirts in a drawer example. Suppose I want the probability of getting a blue shirt. Then my event is getting a blue shirt out of all the shirts in the drawer. So if there were 4 blue shirts, then my event would consist of the 4 outcomes which were getting each of those blue shirts. What is the complement of an event? Well, it's another event which takes all the outcomes not in this event. So if my event was getting an even number, the complement would be not getting an even number, or in this case getting an odd number. So the event would be the numbers 1, 3, and 5. What is the complement of the event? Getting a blue shirt. The complement is not getting a blue shirt. So it would constitute all the shirts that are not blue. What is the probability of an event? The probability of an event is the chance that this event can occur. As we saw, the probability of getting a blue shirt was the number of blue shirts divided by the total number of shirts, which is essentially the number of outcomes in the event getting a blue shirt divided by the total number of outcomes. And the total number of outcomes is represented by the sample space. So simply put, the probability of an event is the number of outcomes in that event divided by the total number of outcomes in the sample space. That was a mouthful. Let's look at some examples and consolidate this information. So here's the experiment, tossing a fair coin. So I'm tossing a fair coin once. What are the possible outcomes? heads and tails. There are two outcomes. So what's the sample space? It's the set of all outcomes. So it's the set consisting of two elements, heads and tails, or H and T. Give me an event. Getting ahead. So the event is the set H. What's the complement of this event? Not getting ahead. So it's the event tails in this case. What's the probability of the event getting ahead? It is the total number of outcomes in the event getting ahead divided by the total number of outcomes in the sample space. So in this case it is 1 over 2 or 0.5. So the language isn't too bad. It's just a systematic way of understanding what's happening. Let's move on to a slightly more complex experiment. We're tossing two fair coins. So I'll quickly list the outcomes. Head, 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 tail, tail, head, tail, tail. Of course, you know all this because you've already studied permutations and combinations, and our lectures on that topic have covered all these examples. So what's the sample space? It's the set of all possible outcomes, and I lazily put curly brackets and I'm done. What's the event I'm looking at? Both land heads. So both tosses give me a head. So let's call the event A. The event A is just HH. What's the probability of event A? So I write it as P of A, which is the number of outcomes in event A, which is just one outcome, HH, over the total number of outcomes, which are 4. It's 1 over 4. Nothing dramatic here. We've seen this many times before. How about event B, which is one lands heads and the other tails? So in how many ways can you get one head and one tail? Let's look at all the outcomes and identify those which are one head and one tail. There are two. There's an H and a T, and a T and a H. So the probability of event B is 2 over 4. Sticking to the same experiment, tossing two fair coins. Event, at least one lands tails. So remember the sample space was HH, HT, TH and TT. And the event in this case, I'll call it C, is at least one lands tails. At least one lands tails. Let me look at all the outcomes that have at least one tails in them. They are HT, TH, TT. So the probability of event C is simply 3 upon 4. Is there an easier way to find this? Yeah, at least one lands tails. So this is a big hassle. I have to look at all the outcomes that have tails in them. What if there were, 15 tosses or 100 tosses? So I'll think of doing it another way. I'll think of the complement of the event. So the complement of the event C, let me call it C bar, is interpreted as none of them land tails. So none of them landing tails would be all landing heads, and that's easy to identify. There's only one way all can land heads. So the complement of the event is just heads, heads. Right? So if I know the complement of the event, it's easy to work back to the event. We'll see this a little later. Let's look at the situation when we toss 3 fair coins. Again, the outcomes. Okay, a quick recap from from permutations and combinations. How do I count the total number of ways I can toss 3 fair coins? So use the multiplication principle. Each toss gives me 2 possible outcomes. So we have 2 times 2 times 2 equal to 8 possible outcomes when we toss 3 fair coins. Let me list them. Sample space has 8 outcomes. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. That takes care of the 4 outcomes that begin with a head. That is, the first coin landed head. Then I'll go tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. These are the 4 outcomes where the first coin lands tails. That covers the 8 outcomes I was looking for. So we have our sample space. Event 1, A. First 2 land heads and the third lands tails. Well, everything is specified. So the only outcome that can satisfy this event is heads, heads, tails. That was easy. Probability of A is 1 out of 8. Event B. 2 land heads and 1 lands tails. Okay, so let's identify all those which have 2 heads and 1 tails. Those outcomes are heads, heads, tails, heads, tails, heads, and tails, heads, heads. Probability of event B is 3 out of 8. Okay, let's switch to another kind of example. If x and y are 2 positive integers and x plus y equal to 5. What's the experiment here? It's not clear to me. So I need to go to the question to figure out what the experiment is. Then what is the probability that x equals 1? So the experiment seems to be, under the given conditions, pick x and find out what x can be. So, the possible outcomes of this experiment are finding out all the possible values that x can take. To find out all the possible values x can take, I need to figure out all ways that I can pick 2 integers x and y that add up to 5. 2 positive integers. So here's x, here's y. So since they're positive integers, I can go 1 and 4. Or I can go 2 and 3, or I can go 3 and 2, or I can go 4 and 1. These are the 4 ways I can get a sum of 5 when I use 2 positive integers. So again, what's my sample space? Since the question asks what is the probability that x equals 1, my sample space is all possible values of x. So my sample space is 1, 2, 3 and 4. All possible values of x. What is the probability that x equals 1? So my event is, let's call it the event A, is picking the value 1. So what's the probability? The probability is obviously 1 over 4. Interesting question. We first had to find the sample space by satisfying the condition given in the question that x plus y is 5 and x and y are both positive integers. Once we had the sample space, which had to be inferred from the question, we knew that it referred to all possible values of x. So we had the sample space as 1, 2, 3, 4. Then the question became easy. So here it wasn't the question that was difficult, it was figuring out what it was that we had to examine. Okay, we've seen this before. Let's study it formally. The probability of the complement of an event. As we saw, the complement of an event is all the outcomes that are not in that event. Suppose we have an event A, which is a subset of the sample space. Then the event A dash, which is its complement, will consist of all the outcomes that are not in A. Well, If I join event A and event A dash, I will get the entire sample space. So to calculate probability of the complement, knowing the probability of the event should be enough. And that's exactly what happens. The probability of the complement is 1 minus the probability of the event. Let's see why this is so. So let's say event A has NA outcomes and the sample space has NSS outcomes. So how many outcomes would the complement have? So the complement A dash would have NSS minus NA outcomes in it. Now, we know that since it's the complement, it consists of all the outcomes that are not in A. So we know that NA plus NA dash will give us the entire sample space. So NA plus NA dash is NSS. The number of outcomes in A plus the number of outcomes in A dash is equal to the total number of outcomes. I divide throughout by NSS. NA by NSS is simply the probability of event A, and A dash by NSS is the probability of event A dash, and NSS by NSS is the probability of the event, the sample space, which is of course 1. Because if you're looking for the probability of the sample space, you're basically saying what is the chance that any outcome can occur, and of course one of the outcomes has to occur, so the probability is 1. And we have the result we want. PA plus PA dash equal to 1, or PA dash is equal to 1 minus PA. So let's go back to an example we saw earlier. The experimenter is tossing 3 fair coins and the event is at least one lands heads. So remember the sample space. The size of the sample space was 8 and the event at least one lands heads. So I got to list all the outcomes and figure out which of them have, some will have 1 head, some will have 2 heads, and some will have 3 heads. That's a hassle. So let's look at the complement of the event. So let's call this event A. And I look at the complement of A is none land heads, which is another way of saying all land tails. So how many outcomes are there in event A dash? There's just one outcome, all tails. So the probability of A dash is 1 over 8. So now we know the probability of event A, at least one lands heads. We know that PA is equal to 1 minus PA dash, which will give us 1 minus 1 over 8 equal to 7 over 8. So the probability of getting at least one heads is 7 over 8. This is a very powerful method of handling questions where the number of outcomes is too diverse. Suppose there were 75 coins and you had to do this. You would have to actually first find out, okay, the total number of outcomes is 2 raised to 75. And then how many of them have at least one heads? Imagine listing out all those 2 raised to 75 outcomes and picking all of them that have at least one heads. The complement is much simpler to express. It is none have heads. So all, in this case, all have tails. And there's just one outcome. So calculating the probability of the complement becomes much easier, which leads us directly to the probability of the event desired. Questions that have at least one in them are much easier solved using the complement, because the complement of the phrase at least one is none, and that's an easier thing to handle. We toss n fair coins. What's the probability that k of the coins land heads and the rest land tails? We need to go back to our permutations and combinations. What's the total number of outcomes when we toss n fair coins? Well, the 2 choices for each toss And by the multiplication principles, it's 2 times 2 times 2 n times, which is 2 raised to n. So n sample space is 2 raised to n. The number of elements in the sample space is 2 raised to n, or there are 2 raised to n different outcomes. We want the event when k land heads and the rest land tails. Okay. So what do I need to count? I need to count those outcomes when k of the coins will land on a head and the other n minus k will land on a tails. So I'm going to put my n coins and I want k heads, any random k are heads, and the rest are tails. Tails. So how do I go about counting this? So I have n slots in all, and I want to choose k of those slots. Every such choice of k slots, I then plug in with heads, and I have my k heads. And of course, by default, the rest of the n minus k slots will have to be given tails. So what am I doing? I'm picking k slots out of n slots. And that answer we all know is n choose k, or n k. So we have our answer. The probability that we are looking for is n choose k over 2 raised to n. That is the probability of the event that k of the coins land heads and the rest land tails. For people who have a difficulty following the notation n choose k, please refer to our lessons on permutations and combinations. Okay, let's look at another very popular example. So we have a pack of 52 cards, a standard deck of 52 cards. We all know what these 52 cards are. There are 13 of each suit. The suits are called spades, diamonds, hearts, and clubs. There are 13 of each suit. And the 13 cards run from an ace, king, queen down to a 2. So you're drawing one card from a standard deck of 52 cards. If you're drawing one card, that means you have 52 different outcomes. So n sample space, let's just establish it in the beginning, is 52. I have 52 different outcomes. Find the probability that the card is a spade. Out of these 52 cards, there are 13 spades. So the probability of getting a spade is 13 over 52, or 1/4. Find the probability that the card is not a face card. So what are face cards? Face cards are the king, queen, and the jack. Because king, queens, and jacks have faces. And there are 4 suits in all. Each suit has a king, a queen, and a jack. So there are totally 12 face cards. There's a king, queen, and jack of spades, a king, queen, jack of diamonds, and so on. So we have totally 12 face cards. Find the probability that the card is not a face card. So I'm going to use the method of the complement. I'm going to find the probability that the card is a face card. Probably that it is a face card, n face card. I'm sorry, this should be p face card. Let's just erase it and p face card would be 12 over 52. So the probability that it is not a face card, that's p not face, would be 1 minus 12 over 52, which is 40 over 52, which I leave to you to reduce to your heart's content. So again, we use the complement to simplify the question. Recall this question studied thoroughly in permutations and combinations. We are now tossing two fair die, find the sample space. So by the multiplication principle, I know that the first fair die can land in one of 6 ways, and the second fair die can land in one of 6 ways, and I'm allowed to take any outcome of the first die with every outcome of the second die. So I multiply them out and I get 36 outcomes. So the sample space consists of 36 outcomes. How do I list them in a sensible manner? So the first outcome could be a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And the second outcome could also be a 1 or a 2 or a 3 or a 4 or 5 or a 6. So I take ordered pairs. For instance, if the first die landed on a 3 and the second on a 5, I'll refer to it as 3, 5. The first landed on a 4 and the second on a 1. This is the first toss. This is the second toss. Then I get 4, 1. If the first landed on a 5 and the second on a 3, then I would get 5, 3. Note that 5, 3 is different from 3, 5. And I totally get 36 outcomes listed in this table or in this matrix. And here we have it neatly done for us. So you see that the outcomes go from 1, 1 all the way to 6, 6. So we'll use that sample space for the next few examples. So we're tossing two fair die. Find the probability of getting both even numbers. Okay. So one way is to list this table out and then mark out all the outcomes that have both even numbers. Let's see if we can use our knowledge of permutations and combinations to quickly calculate this number without listing all the outcomes. So well, anyway, I know my denominator, it's NSS is 36, and I want both even numbers. So I want an even number in the first row and an even number in the second row. How many even numbers are there in the first row? Well, there are 3 choices of even numbers in the first row, and there are 3 choices of even numbers in the second row. And since I want both even numbers, I want an even number and an even number. By the multiplication principle, I get 9 outcomes. So the probability both even is 9 out of 36 or 1/4. Does that sound reasonable? 2. Find the probability of getting a sum of 6. So here the table would be very useful. I just mark out all the outcomes that give me a sum of 6. Or I quickly list them again. Probability sum of 6. Or rather, number, or just the event sum of 6. So the event sum of 6 would consist of the outcomes. Let's start with the lowest number on the first die. So that's a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, and a 5 and a 1. I can't do 6 and 0 because I don't have 0. So there are 5 outcomes that give me a sum of 6, and the probability of sum 6 is 5 over 36. So to do this question, we actually had to list out all the outcomes. There was no clever permutation way of doing it because we were adding the 2 outcomes. Okay. Interesting. Drawing 2 cards with replacement from a standard deck of 52 cards. What's the big deal about this with replacement? It means I draw a card from the deck, I look at it and I put it back, and then I draw the second card from the deck. I don't keep that first card aside. So, how many different outcomes are there? That's always the first question we ask in probability. which is always the first question we ask in permutations and combinations. 2. How many different ways can this event happen? So, or rather this experiment happen. So you're drawing 2 cards with replacement. So well, when I draw the first card, I have 52 possible outcomes. Then I put back that card. So when I draw the second card, I still have 52 different outcomes. And I'm allowed to pair each outcome from the first card with each outcome from the second card. So I have 52 times 52 equal to 52 squared total outcomes. And this is the size of my sample space. NSS is 52 squared. Find the probability that neither card is a diamond. So let's count no diamonds. So the first card cannot be a diamond. In how many ways can I pick a card that isn't a diamond? Well, there are 13 diamonds out of 52. So there are 39 cards that are not diamonds. The second card can't be a diamond either. So I have 39 choices for the second card. So totally I have 39 times 39 equal to 39 squared outcomes where neither card will be a diamond. So this probability is P no diamonds. 39 times 39 over 52 times 52. That's 3 over 4 times 3 over 4 equal to 9 over 16. The second question, find the probability that the 2 cards are of different colors. So, this deck consists of 2 colors. There are 26 cards that are black and 26 cards that are red. The black cards are the suits, spades and clubs, and the red cards are the suits, diamonds and hearts. We need to find the number of ways we can pick 2 cards that are of different colors. So we need to pick a black followed by a red or a red followed by a black. In how many ways can we pick a black followed by a red? There are 26 black cards times 26 red cards, since each black card can be paired with each red card. Similarly, a red followed by a black, there are 26 red cards times 26 black cards. So there are totally 2 times 26 times 26, since we need to add these 2 separate ways of getting one black and one red. The total number of outcomes we're looking for is 2 times 26 squared. We just divide out this number by 52 squared and we get the probability that the 2 cards are of different colors. Let's just do this in this corner. 2 times 26 squared over 52 squared is 2 times 1/4, which is half. So the probability of getting 2 cards of different colors is half. You can try the question, find the probability of getting 2 cards that are both red, and the question, find the probability of getting 2 cards that are both black. Staying with this experiment, drawing 2 cards. No, we aren't staying with this experiment. We're actually doing a very different experiment. Drawing 2 cards without replacement from a standard deck of 52 cards. So here's the subtle part. We're drawing 2 cards without replacement. That means I draw a card, I don't put it back, and then I draw another card. So I've drawn 2 cards without replacement. What do you think the sample space here is? I'm drawing a card and I'm drawing one more card. So I'm drawing 2 cards. So let's count the sample space. I have 52 choices of the first card and I have 51 choices for the second card because I haven't put back the first card. And any of the 52 choices of the first card can go with any of the 51 choices of the second card. Can they? So say I got an ace of spades in the first card and a king of diamonds in the second card. So that's one outcome. However, this could have happened another way. I could have got the king of diamonds in the first card and an ace of spades in the second card. And finally, when I have those two cards in my hand, there is no way of knowing that I got it the first way or the second way, because here I'm drawing two cards without replacement. So the order in which the two cards came out does not matter. So we need to correct this 52 into 51 because we're overcounting each outcome twice. So we divide by 2. So the total number of outcomes is actually 52C2 or 52 choose 2. Choosing two cards from 52 cards. Find the probability that both cards are clubs. The event is both cards being clubs. How many clubs are there? There are 13 clubs and I need to choose two clubs from 13. So, and both clubs is 13 choose 2. There will be 13 choose 2 pairs where both will be clubs. So the probability is P both clubs. 13 choose 2 over 52 choose 2. That's 13 into 12 upon 2 over 52 into 51 upon 2. It's 1/4, which is 1 over 17. So there is a 1 in 17 chance that both the cards are clubs. Find the probability that the two cards are of different colors. So I'm going to now do the complement of the event. I'm going to find two cards are of the same color. So let's find out both black. That's easy. That's like doing both clubs. And both black would be 26C2. Because there are 26 black cards and I want to pick 2. What would be N both red? That would also be 26C2. So the probability of both being of the same color is 26C2 plus 26C2. And then to get the probability that they are of different colors, I do 1 minus this probability. I'll leave the details to you to complete. Discuss the two cases, drawing two cards with replacement and without replacement. So we saw two experiments using a pack of cards. We were drawing two cards in both of them, but in the first experiment, we were replacing the first card and then drawing out the second card. So the number of outcomes was 52 times 52. In the second case, we were not replacing, so we were drawing both cards together, as it were. We were choosing two cards out of 52, and the number of outcomes became 52 choose 2. 52 choose 2 were the different pairs of cards we finally got. So let me write that down. In the first case, N replacement was 52 times 52. N without replacement was 52 choose 2. There are many other important differences. In the first case, whatever you got in the first drawing really has no bearing on what you get on the second drawing because you put that card back and you're starting from scratch. In the second case, however, what you get in the first drawing affects what you get in the second drawing. You can't get that card again. The outcomes where you get the same card twice are not part of the equation anymore. The sample space is much reduced. You cannot get an ace of spades and an ace of spades. So the two sample spaces are very different. Let's look at the theory of odds, which is just another way of expressing probability. So we often hear, okay, the odds for India winning a test are 3:5, or the odds against something happening are 2:6. What do these terms actually mean? Let's link them to probability as we know it. So suppose the probability of team A winning a football match is 2/5. Find the odds for team A winning. So I'll write the probability 2/5 as a ratio, 2:5. The probability of team A winning is in the ratio 2:5. So what's the probability of team A losing? Or rather the complement of the event. So I have an event PA which is 2/5. Then the probability of the complement of the event is 3/5. In this case, of course, the complement is interpreted to mean that team A either draws or loses the match. So the probability of team A not winning is 3/5. Now the odds for are basically the ratio of PA to PA dash. So in this case, it is 2/5 is to 3/5, which is the same as 2:3. So if you have the probability of an event, the odds for that event occurring are the probability of A to the probability of A complement. So in this case, if the probability is 2:5, the odds for are 2:3. The odds against are just found by reversing the ratio. If the odds for are 2:3, then the odds against are 3:2. That's all. So you can interchange your language to use the language of odds for, odds against, and probability. They all mean the same thing. You just have to do some simple manipulation to go from one to the other. So let's look at some simple examples. Suppose the odds for rain tomorrow are 3:1. Find the probability that it will rain tomorrow. So odds for, that means PA to PA complement. So that ratio is given as 3:1. Writing that as fractions, the probability of PA can be written as 3/4. And the probability of A complement can be written as 1/4. And we're done. The probability that it will rain tomorrow is 3/4. Suppose the odds against you getting a raise are, so odds against. The odds against you getting a raise are 4:5. Remember that odds against is A complement is to PA, is that ratio. So that's 4:5. So my odds for is 5:4. That's PA is to PA dash. If my odds for are 5:4, I write them as fractions as 5/9 and 4/9. Because those fractions add to 1. And now I have my probability for getting a raise. It's 5/9. So I just have to convert a ratio to a fraction or a fraction to a ratio to convert from probability to odds. And keep in mind the subtle difference between odds for and odds against, which is just talking about an event or its complement. So this ends our discussion on the basics of probability. In the next class, we will study conditional probability and maybe look at Bayes' theorem.